Okay. Alright, so at the end of the last section, this is where we were. Some examples to finish off that section. 1.2. We actually went out of order a little bit. I believe we started this one. And we didn't finish it because I went off on a rant. So let's actually complete that one first. So we saw this, x plus h minus radical x all over h. I believe something like that was on the first quiz. And we remind ourselves that the way to do something like this is to quote-unquote rationalize. And we rationalize by multiplying and dividing by the conjugate. The conjugate is going to be the same thing with a different sign in the middle. And as you might recall, the real reason why we want to change the sign in the middle is because we want to take advantage of the difference of squares formula. We want to look like a minus b times a plus b. This will allow us to square both terms, hence getting rid of the radicals. Right? So you wouldn't put the same sign, you put a different sign. This guy was called the conjugate. So if you want to get rid of radicals, it's called the conjugate. Now a lot of times students might see a radical, they might freak out and want to get rid of it. They just square everything. You can't just randomly square something. It's not. We'll talk about that pretty soon. But here, you can deal with this by multiplying and dividing by the conjugate. What's going to happen is the numerator becomes a difference of squares, so you realize it's going to be the first one squared minus the second one squared. You're going to have this. I don't remember if I said this before, but whenever you're simplifying a fraction like this, never expand the denominator. You always want your denominator in factored form. Because ultimately you want to simplify something by canceling stuff. You can only cancel across multiplication. Therefore you need things to be in multiplication mode, right? Once you expand, you now put addition in between every term, and you can't cancel in that situation. So you always keep the denominator factored. Now you might for a time expand the numerator, but the goal there would be to expand things so you can kill things and then refactor it. Okay? But you never expand the denominator. At this point, there's not much to do with the numerator. X minus x goes away, and we're left with h over h. And now that would cancel. And so 1 over the radical of x plus h plus x would be your answer. Now we'll talk about this a little bit more when we get back into functions, but you might notice that this guy has a form that we spoke about, I believe, in the first lecture. F of x plus h minus f of x over h, where here, in this situation, your f of x is actually the square root of x. And we said whenever you want to simplify a difference quotient, the goal is to cancel that h in the denominator, which is why we keep going until we cancel that h in the denominator. So that would be the correct way to do that one. And so on the quiz, the similar problem to this will be worked out in this way. Okay. Any questions on this one? How would you, well, F2 seems to be an easier version, but how would you simplify that if you want to rationalize the denominator?
Multiply by radical b over radical b.
Right. And this is something we'll also look at soon when we're going through these. Again, we multiply by radical b because the idea is when we multiply these, we're going to get a b squared, and that's going to kill the radical. And so the conjugate is just the thing that you multiply by to simplify matters. Now, in that case, you're going to have a plus 2 times radical b over just b, and this will be considered rationalized. Now again, like I said, in general we don't care if there's a radical in the denominator. This is just an exercise to get you used to manipulating things. You might notice here, sometimes you want to rationalize the numerator, right? Which is what we did. Sometimes you might want to rationalize the denominator. Just depends on what the point of the calculation is. But in general, there's nothing if there's a radical in your answer in the denominator. I don't care. In fact, this is the perfectly acceptable answer. There are 2 radicals in the denominator. It's totally fine. The funny thing is, if you were to rationalize this, you'd get back to that, which is not the state we want it to be. So hopefully there are no questions there. So that takes care of F. Now let's go backwards. Let's actually go in order this time. We're going A, B, C, D, E, and hopefully we pick up some lessons along the way that we may have forgotten, or maybe we're going to see for the first time. Where is the eraser? It's not exactly for this board, but if any of you become teachers, I can tell you one thing. The thing with being a teacher is Murphy's Law works doubly against you. Right? So when you're a student, you say, oh, I can do this last minute, I'll print out my yeah, when you're a teacher, no. Something, if anything can go wrong, it'll go wrong. Like there's gonna be no eraser, no chalk, so I always carry my own chalk, my own markers. Like whenever I'm writing on a whiteboard, I have like 20 markers, and my students are always like, why do you bring around so much markers? You don't understand. If I only brought 2, you know what's gonna happen? it's definitely gonna, like Murphy's Law can't get over 20 markers. It can get over 2, maybe even 5. But it's gonna like no eraser, yeah, you have it right here. Like everywhere I always have eraser. Okay, let's actually go to A. Okay, so we want to simplify this. So minus 2 over n to the minus 3.
5.
5. Okay. What do we do?
Multiply.
Yes.
Multiply the power.
Right. So we looked at laws of exponents. You can multiply the powers for pretty much all of them. So here you get m times to the minus 12 power. Here you get m to the 12 power. Here you'll get m to the minus 15th power. Now what?
I'll change places.
Just add.
Cancel.
Add the powers.
You cancel.
Well, you can add these, right? And they'll literally become m to the 0, which is going to be 1. I'm going to get to that whole switching places thing. You can have here. Yeah, I got something for you right there. Now, technically, I probably won't care unless the instruction specifically asks you to do something a certain way, but either of those will be fine. Hopefully there are no questions there. If you have questions, just stop them. A to the 16, B to the 8, C to the minus 12. Okay, how does this simplify?
Change the real power to fraction.
You can change the power to a fraction, sure.
Just divide the power.
Hopefully you know that would be how you do it. Now what?
Distribute.
Right, now remember you can distribute powers across products. So I can just multiply 16th by a quarter. So that's a to the 4th. Multiply this.
B to the second.
B to the what? B to the 2. Right? So you said second. I thought you said 7. Okay. What are we doing? Okay, and C to the minus 3.
Or 1 over 6.
Again, I don't particularly care if you leave it like that. But if you're practicing in your textbook or something, they might have the answer in that form. to the 4, y to the 5th. This one's not that crazy. I would have made this one a little bit crazier to illustrate the point. So how would you do that?
Simplify.
What would your first step be?
You address what's inside the parentheses.
Right, PEMDAS, you're going to work inside the parentheses. Now, technically, it's not illegal for you to take this 5 power and start distributing to everyone. 48 to the 5th power? No, not today. Okay, so you'd probably want to start to work on what's inside the parentheses first. Okay, and so here's how I'd rather you do it. I mean, this one is not going to bring the point home as well as something slightly more complicated will. But you would even read in some textbooks, and there's this idea that, okay, having a negative power means you can switch positions. I could throw this guy up there, and if there was a negative power up here, I can throw it down here. I have issues with that method because sometimes when there are several negative powers all over the place, we have students kind of trying to switch things from the bottom while simultaneously trying to switch things from the top, and they make a lot of mistakes when doing that. What can I say? Right? So this idea of switching something or just move this here, like, because there's this fixation, I have to have positive powers. If it's a negative power, I need to do something. No, don't care. That's not an issue. Right? I would rather you do it some way like this. Now this step here, intermediate step, you may or may not follow it, but I'm just going to do it to be clear. Whenever you see something like this, right, and you could have a third or a fourth variable, a lot of stuff going on, a lot of negative powers, what I want you to do is I want you to separate like terms. In other words, I'd like you to think of it as this way. Put the constants together, put the x's together, put the y's together, right? Separate everybody, put them in different positions. So this is going to be 48 over 24 times x to the 4 over x times y to the 5th over y to the minus 2. So now you're kind of separating things in your mind, and psychologically it actually makes things a lot easier. But also just the sheer mechanics of it is going to be easier to not make a mistake. Now, with the numbers, usually students don't mess up there. You can start to reduce here, and you'd reduce to get what? 2. Okay. So now, when you're looking for the rest of them with the variables, what I would rather you do, rather than start switching people jumping up and down, just write down the bases and work on just what the power should be according to your exponential rules. Just know that whatever is here is going to be subtracted whatever is down there. Don't worry about who's negative, who's positive, it doesn't matter. Just put the base x, because an x appears here, that minus that.
3.
So that's a 3. This minus that. That's a 7. Okay? You'll make a lot less mistakes rather than you just switch things, especially when there are a lot of variables and a lot of negative powers spattered all over the place. I've seen students make very silly mistakes who I know otherwise know better. So don't worry about moving things all the time, all over the place. And don't be so frightened by negative powers. Just apply the rules. Here we can apply the laws of exponents. Right? The section is exponents. So at this point, let's do this right here. So now what can we do? Now we can distribute this power across the sum. So that just becomes 2 to the 5th, x to the 15, y to the 35. In other words, that's 32 x to the 15. With a much messier problem, you'd see the importance of doing it this way, but let's move on. Okay, how do you simplify a sum of radicals? Huh? Yeah, 2 to the 5th. Yeah, so how do you simplify a sum of radicals? What do you do?
Factor out the
That's
first
basic
one.
still a lot of
Come again?
Factor out the first one.
I didn't hear you. What would you do with this?
Factor out a perfect square.
Factor out what?
Radical 16 and radical 4.
No, I would factor out a perfect square.
Which is
No.
4.
Yes, you're gonna. 20 is 16 plus 4. You don't want plus, right? Because the radical can't distribute across a plus. So you remember that. Can't distribute a radical across a plus. You want to break these down into multiplications, such that perhaps one of the factors, you can actually take the square root of it and get a nice number. So probably how I would think of the 20 would be to think of it as radical of 5 times 4, right? Because I can distribute the radical across the product. What about 80? 16 times 5. And the 45? It's 9 times 5. I'm not really putting anything in order here. Now, a lot of you can jump right away to what this should be. I'm going to write an intermediate step here, which for something like this, you might not need it, but for something like this, I think it's a very helpful step, so I'm going to write it here. Actually take the time to distribute the radical across each of these guys. And now you can start to simplify things. So radical of 4, you know, what's that?
2.
That's 2, so we're left with 2. Radical 5 here.
4.
That's 4. Radical 5.
3.
And that's 3 radical 5. Now you notice that all of these guys have radical 5s attached to it. That shouldn't scare you, just it's like you had 2x minus 4x plus 3x. 2 apples minus 4 apples plus 3 apples, whatever you want to call it. You'll end up with 1 apple, right? And so that's what you would have.
There's always a 1.
Hopefully there are no questions there. Let's move on to E. A square root. Let me start that because I want a little bit more space here. Can I get rid of this?
Yes.
Look at E. A cubed B squared C cubed plus 5BC radical 45 A to the 5th C. And we're assuming that A, B, C are positive here. So when it looks like this, especially when there are a lot of variables all over the place, here's kind of how I would want you to do it. Find that it's nice to have everything separated so you can see it. So whenever you want to simplify a radical that has a bunch of variables in it and things like that, you're kind of going to take your cue from that red line that I put in here, and you want to break that radical into 2 parts. And in the first, under the first radical, you're going to split things into products, but in the first radical, you're going to put everything that would simplify. And in the second one, you're going to put everything that won't simplify. So and we'll see what that means here. That simplified in first, and terms that don't simplify in the second. Or factors probably is a better phrasing to use, that don't simplify. So in the same way, we're going to start to split things into products. So the 20, you want to think of as a product that you know one part you can take a square root of, the other part you can't, right? So 20 would factor into 4 times 5. I would put the factor of 4 here and the factor of 5 there. See what I'm saying? Split it. Things that simplify, put it under the first guy. Things that don't, leave it under the second guy. But I'm splitting these products. Now what about a cubed? How would you split up a cubed?
You would have a
2 and
squared plus a 4.
You can have had a squared here and one factor of a, right? What if this was a to the 9th? How would you split that up?
Just
A to the 8 and a to the 1, right? You want to, this is 2, you want to make sure you're splitting it up in such a way that the power is divisible by 2 goes into the first radical, and the power that's left over should be less than 2, right? So if you have a to the 9th, you wouldn't split up into like 4 and 5, because 5, if you put that over here, it could still simplify further, right? You want to break it into the smallest possible chunks. Okay, so the a cubed I would split like that. What about the b squared?
just
Well, the whole thing simplifies, right? So I'll put the whole thing over there. There's no factor of b anymore. What about the c cubed? C squared and c is left over here. So that's the first one. Now you do the same thing with the second one. 45,
9 and 5.
9, 5, a to the 5th,
8 to the 4.
a to the 4th, a, and the c.
Just
Just keep it on the side.
Right, c to the first power, that's already less than 2, so that's not going to simplify. Leave it over there. Okay, so that's your first step. Now once you do that, you should be able to start simplifying things right away. Like this is automatically going to simplify, right? Because that 4 is going to become 2, a, b, c, because everyone here take the radical of. This doesn't simplify, so the radical is going to stay attached to that. This one, so we have 5bc times, this will simplify into 3a squared. And then this doesn't simplify, so the radical is still attached to that. And so now we have something like that. Now the first few terms, you can simplify those. So this is 14a squared bc radical 5ac plus this is 15 a squared bc radical 5ac. And what's that? $29, all of that stuff, right? Again, it's like the 5 apples, and right? So it's 14 of this thing plus 15 of that thing. It's the same thing, right? 14 oranges plus 15 oranges. So, if anything we learned today, radical 5 is an apple. Well, this mess is an orange. I don't know how many fruits we're going to go through today, but ultimately you're going to have, you add those 3, you get 29 times this whole thing. A squared bc 5ac. And that would be your answer. Right? But this step is a nice way to break down something like this. Right? So if you have a radical of a bunch of things, that not necessarily numbers, but you have a lot of variables there, and it's all multiplication, just separate the factors into the ones that will simplify under the radical, meaning that whatever number is here, it will divide evenly into those guys, and whoever's over here left over, this number will be larger than the powers that are left over. Once you separate things like that, the first radical will simplify, the second one won't, but after that you can just like add apples and oranges. And that is the last example in this section. So that ends section 1.2. Now we're going to do 1.3, and we're going to spend a while here in 1.3. So this will probably spill over into Monday. It's not anything difficult, it's just there's a lot of things that I want to make sure you guys remember. So we're going to touch on a lot of things, I'm going to rewrite a lot of definitions, and we'll do a lot of examples. So I just want to make sure we're all on the same page. Because algebra is super important. Knowing how to simplify things is going to be very important in this class and in all your future classes. So we should make sure we're doing it right. So right now, we're going to move on to 1.3. So in your textbook, it's titled Algebraic Expressions. Okay, so now I have to define some stuff. Okay. Definitions. We will use the phrase constant to be a member of some domain set we care about. In pre-calc, this is pretty much always going to be the real numbers. Right? So any member of R, we will consider that a constant. Anything that is on the number line, 1, 2, radical 7, minus 3. Anything that you can plot on a number line, we call that a constant. Okay? Now that can vary depending on what your set looks like, but in pre-calc and all the calculus sequence, we pick these guys from R. So these are the constants. A variable, well, this is a letter or symbol that can take the value of any member of a particular set. So we're usually talking about R or a subset of R. This is where our constants live. And a variable is just a symbol that we can allow to take on any value. So I can write down x as a variable and say x is a member of the real numbers, and what that means is you can actually substitute any value, for any constant value, into x at any given time, and the statement that I'm talking about should make sense. That's what a variable is. We also have the following. Term or monomial. Right? So these are interchangeable words. This is a constant times a variable raised to some whole number power. Okay? So for example, 3x to the 7th is a term. Radical 2y to the 9 is a term. Pi x cubed is a term. It's just going to be a constant times a variable raised to some whole number power. We call this a term. Or a monomial. We also have something called a binomial. This is just a sum of two terms. Trinomial was sum of three terms. We can also talk about what we call a polynomial. In one variable is a general sum of terms i.e. An expression. Well, I didn't define expression, but I'll define it later. Of the form a(n) x to the n plus a(n) minus 1 x to the n minus 1 plus a1x plus a0. So an expression like that is called a polynomial, where your ai are constants and your n is a non-negative whole number. So anything that looks like that we call a polynomial. So, example, x squared plus 1, or 2x to the 9th minus 7x cubed minus 4, or 3 3 minus 2x to the 5th are polynomials. Right? They're just x's raised to some whole number of powers that are 0 or bigger, perhaps multiplied by constants. Non-examples. X squared plus 2x minus x to the minus 1, not a polynomial. Right? Or 2 plus radical x, not a polynomial. 0 over x squared plus x squared plus 9, not polynomials. Polynomials are very nice functions. We like them a lot. A lot of mathematics is very nice to deal with polynomials. And polynomials don't have issues that other guys deal with. Like for example, here if you take on x to be 0, that's going to be an issue. Here if you take on x to be a negative number, that's going to be an issue. With a polynomial, there is no such issue. You can plug in any constant and they will produce a meaningful output. So a lot of functions will have issues, but polynomials won't. These are some phrases, so whenever I use any of those words, you should know what I'm talking about. Okay, the idea of a leading coefficient. This is the constant multiplier in a term with the highest power. Okay, so example, if you look at the expression 3x squared minus 7x fourth plus 2x to the ninth minus 9. Then the leading coefficient equals, well, 2. The coefficient is just the number in front of the guy with the largest power. The leading term is what you said would be the entire thing. And by the way, it includes taking the sign with you. So if this was a -2, you would think of it as -2, you would want to keep the signs. So you can have a leading term, a leading coefficient. What else do I want to talk about? Like terms. Lots of things we can only do if they're like terms. When you hear the phrase like terms, what that means is these are terms that differ, perhaps, only in their coefficient. So, for example, x squared 3x squared minus 7x squared pi x squared are like terms. Why? Because their coefficients might be different, 1, 3, minus 7 pi, but the part that's not the coefficient is x squared in all of them. These are called like terms because they are the same except for the coefficients. Now, if you have something like 2x squared, 2x cubed, these are not like terms. Yes, they all have a 2, but I don't care. The coefficient is not the part I care about. The variable part is the part I care about. This is an x squared, that's an x cubed. These are unlike terms. An algebraic expression. This is a set of terms combined via multiplication, addition, or subtraction, of course, division, all the major mathematical operations, division, radicals, yeah, those are called algebraic expressions. So you can talk about a general expression. So like example, 2x squared over radical x plus 12 is an algebraic expression. So I took a polynomial and I divided it by a radical of a polynomial plus a constant. I just took a bunch of things and I combined them via these mathematical operations. We call such a thing an algebraic expression.
Sorry.
Yes?
Sorry, go back. But the leading coefficient is 2y and not 3. Sorry, I just get that note.
Come again?
The leading coefficient is 2 and not 3 because, sorry?
Correct.
I
Are you confused because of the order?
Sorry?
I just exponent this one.
Never mind.
Yeah, so the definition is not who's written first, because that'll get you.
Yes,
The definition is who has the highest power. So the power here is 2, the power here is 4, the power there is 9. I don't care that he's not written first. His power is 9. He's the biggest guy. That's the leading coefficient. Yes?
What's the difference between an expression and an equation?
An equation is two expressions connected by an equal sign that claims that they will return the same result upon the same plugging in. So maybe we can, since we're here, we have an entire another section on equations. Section 1.5 is where we're going to talk about, here's an equation, here's what it means, here's how to deal with them. But since we're here, the question was asked, what is an equation? This is two or more expressions. And by expressions, I mean algebraic expressions connected via this symbol. It must have that symbol in it. Where A equal B means A and B will give the same output when the same variables are plugged in. So it's called an equation if there's an equal sign, specifically. Right? And knowing that is super important. That's kind of, saying it would sound obvious to a lot of people, but it's not obvious when they're actually doing it. So if sometimes they have an expression and there's a radical and people randomly square it to get rid of the radical, that's illegal. And the reason why they should know that's illegal is because they're mixing up an expression with an equation. See, if you have an equation and there are radicals, you can square both sides randomly. If you don't have an equal sign, that is now illegal. And you need to know the difference, right? You randomly square something, there isn't an equal sign, you're wrong. That's basically it. If you decide to square something, there better be an equal sign. You can square both sides, that's fine. But if you have something by itself, you just square it, you now change the value, right? If you just have a 2 right here, square it, it's now a 4, you changed it, right? But if I have x equals 2, and I square both sides, x squared equals 4, that's still a true statement, right? So knowing when you have an equation is actually an important thing. It must have that symbol to have an equation. And that allows you to do certain actions that you would not be allowed to do otherwise. That's very important. That's why I'm going over some of these terms. Because sometimes people aren't as familiar with these terms as they should. They kind of know, but they don't really know. Because if they really knew what these things were, they would know, I cannot do that here, I can do it here. But Evidently, students don't always know that. Okay, let's talk about addition. Specifically of polynomials. In principle, this works for anything. So you can apply it to general expressions if you're very careful. So we can add, subtract two polynomials by adding or subtracting like terms. So there's the phrase like terms. Addition only works with like terms. If you have unlike terms, addition is not going to work. Okay? So if someone says x squared plus x cubed, what is that equal to? Well, it's x squared plus x cubed. Right? You can't combine it. You can't make it smaller. I mean, you can factor it, but that's not necessarily going to make it smaller. Right? So you can't add those because they're unlike terms. So that's a non-example. An example is if you had 3x squared plus 2x squared. These guys are like terms because the variable parts are the same. The coefficients are different, but it doesn't matter. You can add like terms, and that would be able to combine that into one single expression of 5x squared. We can do that whenever we are like terms. Do one of these on this. These should be easy, but don't want anyone to complain about a lack of examples here. Right beside it. Okay, what's the first one? Alright, these two are like terms. You can combine them by addition. So if 2 apples plus 1 apple is 3 apples. These two are like terms because they're both attached to x to the 0. 7. Okay, what about these?
7x squared.
7x squared because these two are like terms. Plus 3x because these two are like terms. Plus 3. What about this one?
Negative 6x cubed.
Come again?
Negative 6x cubed.
Let's take one intermediate step here. Expand the parentheses. Negative sign. You have to expand the parentheses. This is by the distributive law. We covered that in lecture 2. And so you can rewrite this here. As that. And then that would be, now you can combine like terms. Minus 4x cubed and minus 2x cubed, minus 6x cubed. Plus 2x squared, and there's no other x squared, so that's just 2x squared.
Plus x.
X, there's no other x, so that's just x. And 9, there's no other 9. How would you do D?
FOIL?
So we will follow PEMDAS. PEMDAS says we want to start with what's inside the parentheses. What's inside the parentheses is two expressions. One of them has parentheses, and PEMDAS, we can't really do anything here because these are unlike terms, so nothing else to do here. But the next thing would be to deal with the exponent. So the first thing you're going to do is expand. Keep in parentheses here. Don't be sloppy. You can expand and keep those parentheses. What is 2x plus 4 all squared?
4x.
4 squared plus 16x plus 16.
Plus 16. Okay. Now, according to PEMDAS, we still want to work out the parentheses. The subtraction is going to apply here. Right? Because now inside the parentheses, I have a -1 multiplying this expression. Multiplication would come before adding the x. Uh, 5x plus 2. Can we combine like terms now? Yes? X and 16x. Yep, minus 15x minus 4x squared minus 16. Now addition and multiplication, PEMDAS says do the multiplication first. It's going to be minus 30x minus 8x squared minus 2 times 16 is 32. And what can we do here?
Combine like terms.
Combine like terms. 5x minus 30x is minus 25x minus 8x squared minus 32. And that's fine. So that's addition and subtraction. Multiplying polynomials. And in principle, this will work for general expressions. We do this by applying distributive law then combining like terms. And what I mean by applying distributive law, basically what I mean by that is you want to take each term, we know what a term is, it's just one product. Take each term in one expression, multiply by all terms in the other expression. So that's what I mean by apply the distributive law. So let's look at some examples here. So one way to write down multiplication is to just put two expressions in parentheses and put them right beside each other, and that would represent multiplication. So we're going to multiply those. Example, first example, A. Okay, so again, we applied the distributive law. This pretty much looks exactly like what the distributive law would look like, A times B plus C. So we have 2x times x plus 1. This is, take this times that. Laws of exponents would apply when I multiply x by x, so that gives us 2x squared plus 2x. If I look at 3x plus 2 times x minus 5. Here's what I can do. Take the 3x, multiply this. Right, so I'm going to take each term and multiply every term in there. So I'm going to take 3x times this, then 3x times that. Right, so it's going to be 3x squared minus 15x. Then I'm going to move into the middle, multiply this, and multiply that. Take the 2 and multiply everybody over there. Plus 2x minus 10. Now, you might notice this is the first terms that are being multiplied to get here. The outer terms are multiplied to get here. The inner terms are multiplied to get here. And the last terms are multiplied to get here. If you look at the first letter of here, F-O-I-L, you get FOIL, and that's where the rule of FOIL comes from. Because whoever thought of this apparently was way too complicated to remember. Just multiply everything. That's come up with a mnemonic for this. I think it's a pointless mnemonic, but whenever someone says FOIL, that's what they mean. It means to expand two binomials being multiplied. That's specifically what FOIL means. Okay, you multiply the 2 first terms, then the 2 outer terms, then the 2 inner terms, then the 2 last terms. That's what. No, but that only works specifically for this case, multiplying 2 binomials. That's foiling, right? However, if you want to do something like this, it's not called foiling anymore because that's not. You can't really call it that. But anyway, to continue again. So the rule is to apply the distributive law, then combine like terms. So here, there are only 2 like terms, the minus 15 and the plus 2x. It's going to be 3x squared minus 13x minus 10. So that would be the answer there. So for this one, you can FOIL again, but I just decided to throw some fractions in here just to scare people. And to see if we remember how to deal with this. So what would that look like? First term.
3x squared.
3x squared.
Plus 2x. Plus 1 over 3x.
Plus 1 over 3x.
Plus 3 over 2x.
Plus 3 over 2x.
Plus 5.
Plus 1 over 6. Okay, so you know how to multiply fractions, right? Multiply the tops and multiply the bottoms. So you get that. Then we're going to combine like terms, which means you have to combine the 2 middle ones.
2x. 3x squared plus 2x.
3x squared plus
2x.
Say 11 6.
Come on, man.
11 over 6.
Well, 6 is the LCD, so you can multiply this by 2 over 2, multiply this by 3 over 3. That'd be 9 over 6 plus 2 over 6. That'd be 11 over 6x plus 1 over 6. Pro tip here, missing this idea causes people a lot of trouble for some reason, but I want you to be aware that something like 1 over 3x, it's the same thing as saying x over 3, right? The same thing as saying x times 1 over 3, right? Or if you have 11 over 6x, that's the same as 11x all over 6. That's the same as 11 times 1 over 6 times x. When it comes to fractions, it might be convenient at some time to kind of rewrite it in a certain way. You just need to know you can slide things and rearrange the order as long as whoever's on top stays in the top, right? So this is 11 over 1 here, and x over 1. The 11 and the x must always be in the top. But as long as they stay in the top, you can slide them around, move them off, shift the fractions, separate them like that. And the same thing can apply here, right? So you should know that this and this, these are all the same thing. You can shift things and slide things. Multiplication is commutative, and you can take advantage of that in fractions. Okay? Now you do think of this as 11 times 1 over 2 times 1 over 3 times x. Right? This should not be confusing anybody. If it does, you need to practice a few problems to get used to it. You have no idea how simple that will make things. There are certain problems, especially in calculus, where not realizing that you can kind of shift things like that can make the difference between you taking 1 step to simplify something or 5 or 6 steps to simplify something. The mere fact of sliding something off can make so much of a difference. You need to know that you can do that. Okay. There was the last example. A, B, C, D.
That's not weird. Slide. All the white slides all fixed.
Okay, so technically FOIL does not work here because it's not 2 binomials, but how would we multiply these?
X times x squared.
So it's the same thing that we did before. You take every term in one set of parentheses, multiply everyone in the second. So you take x times this, times that. X times x squared, x cubed. X times 12x, 12x squared. X times the minus 1, minus x. Now you move on to the next term, and you're going to do the same thing. Minus 2 times x squared, minus 2x squared. Minus 2 times 12x, minus 24x. Minus 2 times minus 1, plus 2. So that expands it. Now we're just going to see, can we combine any like terms here? So we have an x cubed. It is the only x cubed, so that's gone. We have a 12x squared. We also have a minus 2x squared, so these guys will combine. We have a minus x, we also have a minus 24x. So those guys would combine. I'm striking them off to make sure I don't miss anybody. Then at the end we have a 2. There's no one else to combine that with, so that's plus 2. And that is that expression. By the way, you can literally forget about FOIL and your life would not make any difference. It would make no difference to your life. Just know, take everyone in one thing, multiply everyone in the other thing. That's how we multiply things. I'm not exactly sure why FOILing caught traction. Oh, that's easy. I can remember that. Yeah. Okay, now with this. Oh, no, who's the inner one? Okay. First, outer, inner, last. Then you miss something. You would have totally missed this times that. Okay. Let's continue. So that's how we multiply. Take everyone in one set of parentheses, multiply everyone in the other set of parentheses, collect terms by combining like terms. If you have fractions, you can rewrite the order of the symbols that appear in it, as long as you keep things on top, keep things in the bottom on the bottom. No social mobility here. Let's see. Okay, now these I sort of mentioned before, so we're sort of segueing into the factoring section of this chapter. So I'm going to teach you guys how to factor again. Go through all the techniques. How much time do we have?
A lot of them.
I don't know if we can do all the factoring in 3 minutes, but there are spectral products. So there's the idea of a perfect square. So this is, if you have a plus b all squared, this is called a perfect square, or a minus b all squared. This is called a perfect square. Now that we know how to multiply, we know that this means a plus b times a plus b. Expanding by this method, we would end up with a squared plus 2ab plus b squared. And here we'd have a squared minus 2ab plus b squared. So these are called perfect squares. You should know how to multiply them rapidly. So example, I have 2x minus 1 all squared. You should immediately be able to get to 4x squared minus 4x plus 1 without too much trouble. There's also what we call the difference of squares. And this is the idea that the expression a minus b times a plus b via multiplication, as we just learned it, will give us a squared minus b squared. Well, technically it will give us a squared plus ab minus ab minus b squared, but you have the plus ab and the minus ab kill each other, and you just get this, which you have a difference of square terms. You also have sum of cubes. So this is basically saying that a minus b times an expression like this will end up to be, well, this is technically difference of cubes that I mentioned. Difference of cubes, a cubed minus b cubed. You would also have the expression a plus b times a squared minus ab plus b squared would be equal to the sum of cubes. Sum of cubes. So these are some forms that you should have memorized, and you would apply them in the same way. I don't know, did I do examples here? I think we're okay. So these are special things, and we will be taking advantage of them. So make sure you have them memorized. Now we're going on to the big topic, factoring. Super important. Skill to have is the skill of factoring. There is a theorem in mathematics. It is called the fundamental theorem of arithmetic. Right? So they looked at all of arithmetic and they're like, you know what? What's the one theorem that's the most useful, the most fundamental, that tells us the most about numbers and these mathematical operations and how the universe of numbers are built up? It's called the fundamental theorem of arithmetic, and that is basically the theorem that says any whole number can factor into a product of primes. Right? So the best theorem in all of arithmetic is a theorem about factoring. It's a very important skill to know. And it'll help you with solving equations, with simplifying expressions. It'll help you with a lot of things. As I mentioned before, factoring is simply the opposite of multiplying out. So for example, with the difference of squares example, if I had a minus b times a plus b, I can multiply this out to get a squared minus b squared. This multiplying out is called expanding. This is expanding slash multiplying out. So if you go from a situation where you have a bunch of parentheses and you remove those parentheses by multiplication and you end up with just a sum of terms, you say you expand it. That's called expansion. Factoring is the opposite of this. Factoring is going the other way. If you have a sum of terms and you want to rewrite it into a situation in which you have a bunch of things multiplying, so here we have two terms, there's a sum, but I want to write two terms as one big term. That's just a multiplication of stuff. That is called factoring. And in this case, the individual terms that are in this expression are called the factors of the expression. So here, a minus b and a plus b are what we call factors. So the expression a squared minus b squared, I can factor that in two factors, one of which would be a minus b, a plus b. So those are called the factors. So whenever you write something in factored form, each individual thing that's being multiplied, you call that a factor in the factored form. Okay. Now, there are a couple of rules that we'll go through, and then by Monday, I will give you like a general rule to factoring, so which is kind of something you want to have in your head. So if I give you a random list of a bunch of stuff and I say factor this, right? Looking at a random problem in your head, there should be a list of things that you would go through in order. You would want to see, can I do this first? No. Can I do that second? No. Can I do that third? There's like a hierarchy of operations that you would attempt to do. And ultimately, we're going to conclude this section with that. But in the meantime, let me tell you about some of the individual skills that you would need to actually do factoring properly. So, one is factoring out the general common factor. This is the first important skill you need to know. So this is general, greatest common factor, sorry. Greatest common factor. It's called the GCF. So remember, a factor is just one of the pieces in this product. So when you talk about the greatest common factor, you're talking about one of the pieces in the multiplication that is common to everyone. And you want to find the largest thing that is a multiplication that is common to everyone. Okay, this is called a GCF. And so this is the largest factor common to all terms in an expression. Now, GCF factoring is what we call factoring this expression out. And this is done by reversing the distributive law while applying laws of exponents. I'll get specific as to what this means. So I can probably show you by doing a few examples. So let's do the first example. I want you to factor these. A. 4 squared plus 4. B. 2x squared y plus 4x y squared minus 2x squared y squared. C. 2x times y plus z minus 3y squared times y plus z plus 5xz times y plus z. 2x to the 3 over 2 plus 4x to the 1/2 minus 6x to the minus 1/2. Now, a key component in factoring all of these is factoring out the GCF. So we want to identify the greatest thing that is common to everyone. How do you find that thing? So, A. So the idea is you want to identify the constants, the common constants or variables. And variables. The GCF is the product of all of these things. Where each is raised to the lowest power to which it appears. Okay, so basically, I go here, I try to identify all the constants or the variables that are in everyone. In this case, you realize that 4 is in both terms here, so that means that is by definition a GCF. You will also notice that this is 4 to the first power and 4 to the first power. We will factor out the lowest power all the time. You will always factor out the lowest power no matter what. So this would become, take the 4 and you have this expression. So you pull that GCF out, you open parentheses, and you write what's left over on the inside. So what will be left over on the inside here?
X squared plus 1.
Right, so you have x squared plus 1. You're reversing the distributive law. Notice that if I multiply out, expand it, I would get back the original. How do you factor this?
You can factor it.
Well, you can't.
Yeah.
Not over the real numbers. Okay, cool. And that's it. That's how you factor that one. What about 2x squared y plus z minus 3y squared y plus z plus 5xz y plus z? What would you do here? What's the GCF?
Y plus 7.
The y plus z. That's the guy that's in everyone. Again, there's only one power. It appears to the first power everywhere. And so you would pull that out to the first power. Open parentheses, you're going to write what's left over after you pulled it off. So we're left with 2x squared minus 3y squared plus 5z. Nothing else here is common, so you can't really factor anything out there. And we would kind of leave it like that.
Skip B.
Oh, skip it. Skip it.
We did C just now.
I did C. E. 2x squared y plus 4xy squared minus 2x squared y squared. What's your GCF here?
2xy.
2xy. How do you know 2? Is there a 2 here?
There's a 4.
There's a 4. So in other words, what you do, you think of that as 2 squared, right? So there's a 2 everywhere technically, even though there's a 4. So you will, so what are the powers of the 2's that appear? We have a 2 to the power 1, 2 to the power 1, 2 to the power 2. 2 appears in everyone. The lowest power is 2 to the 1, so you would factor out 2 to the 1. Now you look at the x's. There's an x everywhere. Power here is 2, power here is 1, power here is 2, 1 is the lowest power. I factor out x to the 1. Look at the y's. There's a y in everybody. Power here is 1, power there is 2, power there is 2, the lowest power is 1. Factor out y to the 1. That's the only thing. Open parentheses, write what's left over inside. Now we have one factor of 2, we pulled it outside, so he's gone. We have 2 factors of x, we pulled out 1, so there's 1 left. We had 1 factor of y, we pulled that out, so that's gone. Move on to the next term. Here we had 2 factors of 2, we pulled out 1, so there's a 2 left. 1 factor of x, we pulled that out, so that's gone. 2 factors of y, we pulled out one of them, so that's 2y. Move on to the next term. 2 to the first power, there's 1 factor of 2, we pulled that out, that's gone. There were 2 factors of x, we pulled out 1 factor of x, so there's 1 left. There were 2 factors of y, so there's actually, we pulled out 1, so there's only 1 factor of y left, and that's that. Okay. What about D? So I believe a problem like this was on the quiz, very similar to it, at least. What's the GCF? Huh? 2x to the what?
To the half.
2x to
2x to the 1/2? Stop laughing. Why is it no? What is the GCF?
Would it just be 2?
Nope. An x is in everyone. So there should definitely be an x factor in the... Well, which x?
The last one.
What's the rule? How do you determine who gets pulled out?
The lowest power.
So pull out the lowest power.
Negative.
What is the lowest power? 3 over 2 minus half, or 3 over 2 1/2 or minus half? Who's the lowest? Minus 1/2. That's who you factor out. You always factor out the lowest power, right? Doesn't matter if it's scary, doesn't matter if they're fractions, doesn't matter if some are negative or positive. Figure out who is most to the left on the number line. That is the guy you factor out, always. So if you see something like this, x to 2, 2 is in everybody. 2x to the minus 1/2 is going to be your GCF. That's the lowest power to which x appears. So you have 2x to the minus 1/2. Now you're going to write what's left over. Okay. So the 2 I pulled out, so the 2 is gone. Here at x to the 3/2, what's going to be here?
Legs.
2.
Huh?
X.
X?
X
X?
is
And then
second.
what?
Squared.
X.
X.
X what?
X squared.
Did you just tell me X? Are you guessing now? No, then you were not sure? What should be here?
So X to the 1?
X to the 1?
Or X to the 2 over 2?
Shouldn't it be a 1 because of the fact that
It should be a 1? Why would it be a 1?
Square
X, shouldn't it be 1 because of the
Because
fact
yeah,
that
it's
you're
1.
factoring 2x, you already have a 2x there, so one that just cancel out to make it a 1. Because of the exponent, I can't go 1.
1.
Yeah?
Wouldn't it be -3?
Negative 3. Now that's a new one. Okay, negative 3. Is it negative 3?
4 over 2.
1 over 2.
4 over 2.
Now we're just random. 4 over 2. Why would you guess 4 over 2?
To make a period.
Okay, so here's what I meant. This is what I meant by you need to obey the laws of exponents. So let's kind of look at this from a different angle. Let's go back to an easy version, really dissect what we're doing, so there should be no confusion moving forward. Factor. What would you do? X cubed. Common term. What do you have left over?
X squared.
X squared plus 1. Why x squared? What happened to make that an x squared?
Plus 2 plus 1.
What happened to the 5 when I pulled out the 3 to turn it into a 2? I subtracted the 3. Why subtract the 3? Well, I know when I multiply things of the same base, I add the powers. Here I'm trying to reverse that process, which means if I'm pulling off a factor, I need to be subtracting the power that I pull off. So what's going to happen is, when you factor this and you get, oh, x cubed times x squared plus 1, what really happened is you did this. You pulled out x cubed and you subtracted the cube from all the powers of x's inside. So now the 5 minus 3, that's an x squared. X to the 3 minus 3, that's x to the 0, that's 1, right? So you're left over with x squared plus 1 because you're subtracting the power that you pulled out. Okay, what should be here? X squared. Why? Because let's write the intermediate step here. The 2 I pulled out, that's gone. Here's an x left over. I pull out a minus half. What should the power be? Well, it should be 3 over 2 minus a minus 1 half. I'm going to subtract the power that I pulled out. Before I move the 2 from here, this is a half, so this is going to be a half minus 1 half, minus a negative 1 half. Minus 3, this is going to be x to what? Minus 1 half minus a minus 1 half. That's what's going to happen. Now you can start to simplify this. This is 3 over 2 plus 1 over 2. That's 4 over 2. That's 2. That's why it's x squared. A half minus a minus half, that's a half plus a half. That's 1.
Minus 3.
Here, we have minus half minus a minus half. That's minus half plus a half. That's x to the 0. That goes away. So that's that. So that's the rule. So the GCF is the guide to the lowest power. It's always the common factor to the lowest power. So among these powers, the negative 1 half is the guy you pulled out. Now it's like a fraction. Oh my God, what do we put inside? I don't know. Minus 3, a half, 2 quarters. No, if you know you should be subtracting it, which by now we know how to subtract fractions, you just realize, oh, it's just going to be all the old powers minus the power I factored out. And so that becomes that. So that's the first, yeah.
If we had a problem like that, do we have to factor again when we get to that point?
Yes. So you should always, that's going to be a part in the general list I'm going to give you, is like, after you apply any rule that you see right away, you should always check the remaining factors to see if you can factor further. Okay? This one can factor further, right? This is going in, this we can become, can you factor this? Can you think of 2 numbers when you multiply, you get a minus 3?
Yeah.
You add them and you get positive 2?
Yeah.
What is it?
Negative 3 and 1. So x minus 3, x plus
Positive 3 and negative 1.
What did I say? Something opposite.
You said the opposite. Okay, so that's what you could factor. Now this here, this is called factoring a trinomial. That's a totally separate skill, and we're actually going to go over it. Okay, so this is a sum of 3 terms. So when we factor it, it's called factoring a trinomial, and we're going to talk about how to factor that with a couple methods. How much time do we have? Maybe. So we'll come back to this probably next time. Maybe something I can get through quicker is actually the idea of factoring by grouping. This is called factoring a trinomial. Okay. We'll cover it next time. Stay tuned for the next exciting episode. Okay, so now let's talk about an idea called factor by grouping. This is used when we have 4 or more terms. Not in the sense that it's guaranteed to work. It might work. It's something you should look for if you have more than 4 terms. Okay? Won't always work, but you should always look for it. You see 4 things. Factor by grouping should be one of the first things you think about. Okay. So here's how this works. This is done, it's called grouping. So what you're going to do is you're going to group terms and factor the GCF from each group, which we now know what the GCF is. hopefully, a common factor, you'll create another GCF. Another GCF will be created in the parentheses. And then you factor that out. That process is called factor by grouping. So sometimes you have 4 or more terms. What you can do is group these terms together and factor out the GCF from each term. Clearly you'd want to group the things in so that you have the same number of terms in each group, so that way you have a hope of getting to a GCF. But hopefully you separated the groups, factor out a GCF from 2 groups separately, and the goal would be to have what's left over in the parentheses be another GCF. It would be the same thing. Let's do an example of that. So for example, 5x squared plus 5x plus x squared plus x. Now that one's kind of silly, because you can actually group like terms, but I just want to illustrate the idea. You could, sure, yes. Just deal with any of the smart Alex out there. You could just combine this and say that's 6x plus this, and you factor out the 6x and then you get x. Okay. Yeah, we know that, but I want to illustrate this, and I'll give you an example that's not so trivial. We'll actually do a couple examples that's not so trivial next time. But I want to be able to talk about this without getting too complicated and not talking about the other things I haven't told you. So the idea is you can think of this as in 2 groups. I can group these guys together, group those guys together. And what I can do is from the first group factor out the GCF, which in this case is what? So that will be 5x times the leftover x plus 1. What about this guy? That's x, the leftover x plus 1. So now here's what you're looking for to happen. What's left over in the parentheses should be the same thing. And what you can do is you can now factor that out. Right? Because now that's a GCF. You can factor that out and you'd be left over with 5x plus x. Now of course 5x plus x is 6x and this becomes 6x plus 1. So at least we know, we have a little verification there. You could have done it another way and get that. But that would be the factor. This idea is called factor by grouping, and it's not always this stupid and obvious to apply. But I just wanted to start out with a stupid example so everyone can follow. Can make this a slightly more challenging problem, and we'll do problems where we have to factor by grouping within doing another problem. But just understanding this idea of factoring by grouping is important enough. Group terms, factor out the common factor, and hopefully you have a common factor left over that you can factor out afterwards. So here you have 5x plus 5y plus x squared plus xy. A little bit more complicated, but not much. Again, there are 4 terms, and now you can't really combine things because they're not unlike terms, all of them. But again, we can think of it as 2 distinct groups having a pair of terms in each. Common factor here is 5. I can factor that out. I'd be left with x plus y plus common factor here. X, can factor that out. I'd be left with x plus y. Now, x plus y is a common factor, which means I can factor that out. And I'd be left over with 5 plus x. So that would be the factoring of that one. So we'll stop there. We'll start next class talking about factoring trinomials. We'll also have a quiz at the beginning of next class. Oh yes, I have quiz to give back. Literally every class I had this week, I forgot to give back the quizzes. Isn't that great? So now I'm walking around with all these papers in my bag. I want to get rid of these. Okay, where are we? So this, what I have to give back is the very first quiz, quiz 1, because I forgot to give you guys that back. Quiz 2 is not done yet. Naomi? Oh, let me turn off the camera. You guys can just grab these and as you're leaving.